This is Step 2, 2014, Question 6. The question begins by asking us to simplify this expression here in order to deduce this result down here. You could do it with the or otherwise way. However, if we're given a hint for a question, we should probably just do it the way they want. But if you're interested, I'm going to put some otherwise methods at the end of this video, so you can see them at the end. Okay, let's jump straight in. We're being told to simplify this expression here, so let's just do that. Colour coding, we have sine of r plus a half x minus sine of r minus a half x, gives us this. I've just expanded these out using the addition formula and the subtraction formula for sine. These are in your formula booklet. Then if we just notice that this sine of rx term cancels with this one, and we've got a minus minus, so we've got plus this term, plus another one of that term, that gives me two lots of it, so I get this. Now, because I'm summing cos of x, it seems wise to rearrange this equation to get it in terms of cos of rx. And therefore we can just write that cos of rx is equal to this, just by rearranging this equation above. Okay, so now how can we deduce the result that we're trying to get at? Well, if we sum both sides over r, from r equals 1 to n, we have this here. Noticing that 1 over 2 sine of a half x is independent of r, and is therefore just a common factor of all the terms in my addition, I can pull it out the front. Now what do we do? Well, the easiest way to see a sum like this is just to write out the first few terms and the last terms to see what's going on. So I'm going to do that now. Notice that all the terms are cancelling out here, except for one of the very first terms and one of the very last terms. Indeed, sine of 3 over 2x cancels with minus sine of 3 over 2x, sine of 5 over 2x cancels with minus sine of 5 over 2x, sine of 7 over 2x will cancel with a minus sine over 7 over 2x over here, and so on. Then when we get to the end of the sequence, we have sine of 2n minus 1 over 2x, well that will cancel with this sine of 2n minus 1 over 2x over here. This term will cancel with something before, so we're just left with that at the end. So the only terms which don't disappear is this minus sine of a half x and sine of 2n plus 1 over 2x. So that just gives us this. And thus we can conclude that the sum from r equals 1 to n of cos of rx is given by this expression here, which is exactly what we were required to show. We define the functions Sn of x for n equals 1, 2, and so on by this expression here. For part 1, we are asked to find the stationary points for S2 of x and to sketch this function. Give this a go yourself now, and when you're ready, return to the video. Okay, so if we just substitute in n equals 2 to our definition of Sn of x, we quickly arrive that S2 of x is equal to this. We want to find the stationary points, so we need to consider the derivative of S2 of x. Recall that stationary points occur when the derivative is equal to 0. So if ds2 by dx is equal to 0, then we have that cos x plus cos of 2x is equal to 0. Recalling that cos of 2x is 2 cos squared of x minus 1, we obtain this line here. If I just rearrange that with the squared term at the front, which is a convention for a quadratic, we have this. And factorising, we can obtain this line here, which finally gives us that cos of x is a half, or cos of x is minus 1. Which in turn mean that x is equal to pi and 3, or x is equal to pi, since our range for x is between 0 and pi, inclusive. Since we're asked to find the stationary points, we also need to find out what S2 of x is at these points. So S2 of pi and 3 is equal to sine of pi and 3 plus a half of sine of 2 pi and 3, which gives us this, which is 3 root 3 over 4. S2 of pi is easy to calculate, since sine of pi and sine of 2 pi are both 0, which just gives us 0. And therefore we can conclude that the stationary points are pi and 3, 3 root 3 and 4, and pi, 0. We're then asked to sketch S2 of x. We are then asked to sketch S2 of x. So, how do we do this? Well, here's our axes, and I've just labelled on the points, which we know are stationary points. So we have the point at pi on 3, 3 root 3 on 4 up here, and we have the point at pi 0 here. So now we want to consider what our function will look like. First of all, does it have any roots? Well, you know that S2 of 0 is certainly 0, and S2 of pi is certainly 0. What about in between? Well, notice that if there was a root in between, so imagine for a second that there's a root, I don't know, say here. Well then, we're going to have something which looks like this, either touching, or we're going to have another root, so our function looks like this. Either way, we've got a turning point here, or a turning point here, since the function is continuous. So we have another stationary point. But we know this can't be the case, because we only have two stationary points. So we can't have any roots between 0 and pi. Finally, since we know that our function has to go up to this point here, and back down, we can conclude that at this point with x equals pi and 3, we have a maximum turning point, and at x equals pi, we're not really sure, so we're just going to try and make it look as flat as possible at the end. So, yeah, if we were to continue, it could go down, could go back up. Not really sure, but we don't need to know, because we only need to consider between 0 and pi. And that concludes this part of the question. In part 2, we are asked to show that if Sn of x has a stationary point at x equals x0, where x0 is between 0 and pi, then this here holds that sine of n x0 is equal to 1 minus cos of n x0, all multiplied by tan of a half x0. We're then asked to show that Sn of x0 is greater than or equal to Sn minus 1 of x0 using this result, and to deduce that if Sn minus 1 of x is greater than 0 in this interval 0 less than x less than pi, then Sn of x is greater than 0 for all x in this interval. Give this a go yourself now, and when you're ready, return to the video. Okay, so how are we going to do this? Well, we know this already from the first parts of the question, so the sum of cos of Rx, and we know that Sn of x is given by this. So since we're considering stationary points, we want to differentiate Sn of x. That makes sense. So dsn by dx, that's just d by dx of this whole sum, which, since it's a finite sum, we can put the d by dx on the inside, so differentiating sine of Rx, we have an r cos of Rx, which gives us the sum from 1 equals to n of cos of Rx. But hang on, we know what that is in the case that sine of half x does not equal to 0. So we can write that as equal to this, for this range where 0 is less than x, less than or equal to pi, because then we have sine of half x is not equal to 0 in this range, and we're good. Okay, so we want to consider a stationary point, x equals x0, where x0 is between 0 and pi. And therefore, if it's between 0 and pi, it certainly lies in this interval that we've specified here, so that we can conclude that since dsn by dx is equal to 0 at x0, we must have the numerator of this fraction is equal to 0 at x0. Now, again, if we use the addition formula on this part for the signs, we can expand to arrive at this. And if we divide through by cos of a half x0, we obtain this line here. How can we be sure this is valid? Well, since we know 0 is less than x0 is less than pi, we know that cos of a half x0 certainly is not equal to 0. Therefore, rearranging this, we arrive at this result here, which is exactly what we wanted. We now want to show that Sn of x0 is greater than or equal to Sn minus 1 of x0. See if you can do this yourself now, and when you're ready, return to the video. Okay, so with most inequalities, if we want to show something, it's most convenient to find the difference. So if we want to show that Sn of x0 is greater than or equal to Sn minus 1 of x0, another way to do that would be to show that their difference, Sn of x0 minus Sn minus 1 of x0, is greater than or equal to 0. That's the approach we're going to take now. So, if we substitute in their definitions for Sn of x0 and Sn minus 1 of x0, we have this. This may look intimidating, but notice that all the terms will cancel except for the very last term is in Sn of x0. This just leaves us with 1 over n, sine of n x0. Now, we've just derived this equation here. So, since we've derived this, and we can't think of anything else to do here, this is probably the best course of action to take. So let's substitute that in here. Then we are left with this result. Now what do we do? Well, we want to show this is greater than or equal to 0. So to do that, we want to show that this part is greater than or equal to 0, and this part is greater than or equal to 0. Conversely, you could also show they're both negative, but that's just not the case here. Since we know that cos of nx naught is less than or equal to 1, we have 1 minus cos of nx naught is greater than or equal to 0. Since we know x naught lies between 0 and pi, we have tan of a half x naught is greater than 0. Therefore, together, this means that their product is greater than or equal to 0, and thus we have this. So we have a Sn of x naught greater than or equal to Sn minus 1 of x naught, which is exactly what we wanted. Finally, we're asked to deduce that if Sn minus 1 of x is greater than 0 in the interval 0 less than x than pi, then Sn of x is greater than 0 for all x in this interval. How are we going to do this? Well, let's think about this. We know that Sn of x is greater than 0. Sn minus 1 of x, sorry. Sn minus 1 of x is greater than 0. Okay, suppose Sn of x has turning points x naught for 0 less than x naught less than pi. Well, then we know that Sn of x naught is greater than or equal to Sn minus 1 of x naught, because we've just done that, and that's greater than 0. So we know Sn of x naught is greater than Sn minus 1 of x naught because of this, and we know it's greater than 0 by this assumption here. So what does this mean? Well, from this, we can conclude that all stationary points must be positive. So all stationary points, and by positive I mean the y-axis, the y-coordinate, stationary points, have Sn of x naught greater than 0. Okay, so what does that mean? Well, then I can't have any roots. No real roots between 0 and pi. And why is that? Because if there was, we would have that Sn of x naught is less than or equal to 0. I hope that makes sense. I'm going to draw a picture in a minute, so just bear with me. So finally, since there are no roots in the interval, and it must be positive at some points, we must therefore have that Sn of x is greater than 0 as well. Okay, if you're still not sure about all of this, let's just quickly draw a diagram. So let's just shrink this a little bit. Okay, so we're going to have something which looks like this. Okay, so suppose our Sn minus 1 of x is something like this. We know it's always bigger than 0. And then suppose that our Sn of x, let's do that in a different colour, let's do that in green. Well, suppose it has, I don't know, some turning points like, I'm going to call them all x naught. It's not great notation, but it's fine. Then we know that Sn of x naught is greater than Sn minus 1 of x naught. So it must be something like this. Let's actually put another one in here. Right. And therefore, since we know these are positive, we must have a function going through here, something like this. I don't know, something like that. Okay, now specifically, we can't cut through the x-axis, or even on it, because then we'd have another stationary point here, and that would be less than, S of x naught there would be less than Sn minus 1 of x naught. But that's just not true. So we can't have this this happening, and that's why we must have that Sn of x is greater than Sn minus 1 of x. Oh, sorry, no, it's just greater than 0, sorry. So we have a strictly greater than or equal to at the stationary points, but in between it might not necessarily be. So yeah, we're done there. Finally, we are asked to prove that Sn of x is greater than or equal to 0 for n greater than or equal to 1 and 0 less than or equal to x less than or equal to pi. This actually follows really quickly from part 2, so see if you can do it on your own now. Okay, so from part 2, we know that if Sn minus 1 of x is greater than 0, then Sn of x is greater than 0 for 0 less than x less than pi. We're also going to note that at the endpoints, 0 and pi, Sn of 0 is equal to Sn of pi is equal to 0. So we certainly have equality in our inequality here. Great. So finally, we just want to show that all the other points will be bigger than 0. Well, let's use what we have here. If we can show that it's bigger than 0 for some n, then we know that will be bigger than 0 for the next one, and so on inductively. So we're going to consider Sn of x for 0 less than x less than pi, and we know that S1 of x is sine of x, and that's bigger than 0 for all x with 0 less than x less than pi. So if we assume inductively that Sk of x is greater than 0 for all x with 0 less than x less than pi, then by this fact here, which we derived in part 2, Sk plus 1 of x is also greater than 0 for all 0 less than x less than pi. Since we know it's true for n equals 1, then by induction we arrive at the result that Sn of x is greater than 0 for all 0 less than x less than pi and n greater than or equal to 1. So if we just put in the fact that the endpoints give us 0, we therefore have Sn of x is greater than or equal to 0 for all x with 0 less than x, less than or equal to x, less than or equal to 2 pi, because we know the endpoints give us 0 here, and we are done. Okay, so as discussed at the start, I'm going to show you some other ways that we can derive the sum from r equals 1 to n of cos of rx. I'm only going to outline these methods, so they're not complete, and you'll have to do some algebraic manipulation to get what you want. But here's the idea. The first method we could use is if we set a is equal to the sum of cos of rx and b is equal to the sum of sine of rx. Then, if we consider a cos of x plus b sine of x and a cos of x minus b sine of x, as follows, we can use the addition formula here to get this, which simplifies to that, which we can write in terms of a, labelling that 1. Then if we consider a cos of x plus b sine of x, we get this. Again, using our addition formulae, we have this, which can be manipulated, again, to give us something in terms of a. So then if we call this 2 and this one 1, if we add them together, we can obtain this here, which rearranges to give us this. And then you're going to need to do some algebra to put this in the form of the question, but this method works. Notice, once we found a, we can also find out what b is quite easily by using one of these relationships here. So this method also works for finding out what b is. Another method we're going to use can also find out what a and b both are, and is perhaps the most simple and most satisfying of all. If you're familiar with complex numbers, this is probably the best method to use if you wanted to find this sum as well in one go. We know that e to the I theta is cos of theta plus I sine of theta. So therefore, if we sum over cos of r theta plus I sine of r theta, that's summing over e to the I r theta. So if we just split this into the real and imaginary part on the left-hand side, on the right-hand side I have the same thing, but to make it more obvious, I've put it e to the I theta all to the power r, which is of course a geometric series, so we can evaluate it like this, provided that e to the I theta does not equal to 1, which corresponds exactly to cos of theta equals to 1, which means that theta is equal to 0. So we're just not having that. So then if we keep going from here, we can then just write in what e to the I theta to the n plus 1 is, and what the other term is. So then, if you wanted to find out what this sum is and that sum is, realising this, so realising the denominator, so the denominator is a real number, and then splitting this into real and imaginary parts, you can just equate the coefficients to get what you want. So realise the denominator, collect real and imaginary parts, and you'll get that cos of r theta is the real part of the right hand side, and the sum of the sine of r theta is the imaginary part of the right hand side. So if you want, give these methods a go now. This one here is my favourite.